Today's lecture is entitled Comets, Links to the Origins of the Solar System, and our presenter will be Dr. Walter Harris from the University of Wisconsin's Space Astronomy Laboratory. Dr. Harris attended the University of Illinois in Champaign for his undergrad program and received his PhD from the University of Michigan in Astronomy, Atmospheric, and Space Sciences. And with that brief introduction, I'd like to welcome Dr. Harris to our lecture this afternoon.
Hello, thank you for listening, and I appreciate the opportunity to be here today to talk with you about a subject that I've spent the last 5 years working on, and that's comets. The title of our lecture today is Comets, Links to the Origins of Our Solar System. And comets are important objects that have a lot of relevance to the origins of our solar system, but they also have relevance that extend well beyond the origins of our solar system. A little bit of background information surrounding comets. It's important to realize that comets are unique objects in that only the sun and the moon actually ever approach the brightness of comets when they really get going. If you remember several years ago, Comet Hale-Bopp was fully visible if you were standing on a street corner under a light in Brooklyn, New York. I can safely say that no other comet in the last 150 years could have said that, and certainly no star and no object other than the sun and the moon could have done that. Now imagine for a moment the history of mankind and most of that time not knowing what a comet is. When an object like that appeared, seemingly at random, and changed in shape and brightness on a daily basis, and then moved rapidly across the sky with respect to the planets and the other stars, well, that was an extraordinary event. And as a result, comets have always occupied a particularly important place in our public psyche. Scientifically, comets live up to the hype. They're very important objects on multiple levels. They are remnants of the early solar system, and they carry a record of the formation and the composition of the early solar nebula. They are also evolving astrophysical laboratories, which allow us to study various things, including the galaxy, the environment between the planets, and the interaction of matter with sunlight. All of these are interesting concepts, many of which we cannot do without comets. And finally, comets have played a very important role in the development of life on Earth and its continued evolution. Today, we're going to address several specific questions in a more general way with respect to comets. Some of the questions that I hope to address today include, what are the different parts of a comet? Where do they come from? How are comets important to our studies of the early solar system and galaxy? And how are comets useful as astrophysical laboratories? And finally, at the end, I want to talk a little bit about the role that comets have played in our popular psyche over the last 5,000 years of human civilization. So moving on, let's get right to the question that a lot of people don't know the answer to but think they do. What are comets anyway? And we all have our own idea based on the things that we've seen on television or in picture books or in the sky itself. We think of comets as a broad, diffuse, roundish sort of a glow, followed by a tail that extends from a small distance to as far as one end of the horizon to the other. And indeed, these are important components of a comet, but they aren't the comet that we actually are seeing. That object is actually very small and very dark. A typical comet is actually nothing more than a dark, icy object about 10 miles across. Now, from our perspective on them, which is typically about 150 million kilometers distant, an object of that size would appear about the same size that a dime would if it were on top of the Madison Capitol building and you were looking at it from downtown Milwaukee 60 miles away. That's not very spectacular at all, and certainly what we're looking at can't possibly be that small icy object. So, what are we looking at? The observable part of a comet, or the parts of a comet that we see, actually can be made up of three different specific elements that define different parts of the way that comets interact with the sun and their local environment. The key element that you need to understand when we're dealing with a comet, and the main reason why comets stand out while asteroids, which are basically the same size, do not, is that comets are made of ice. And ice, when it gets close to the sun, has a tendency to melt. That's what makes comets spectacular. The ices that are comprising the comet begin to melt as it approaches the sun, and it forms all manner of structures. Now, outgassing from the comet nucleus, which is the icy region that I just described, actually can take on several forms. It can, in some cases, be a sort of a uniform outflow from all surfaces of the comet. This will produce a sort of a broad, diffuse gas production, but also comets have a tendency to produce what we could call tightly jetted formations, that is, active sectors on the nucleus that are more effectively melting than other sectors. Those areas will produce collimated jets of gas that can extend tens of thousands of kilometers away from the comet and produce very spectacular features. If you look on the overhead that's attached to this talk, you will see a picture in the lower right of Comet Hyakutake, which is a comet that had many jet features attached to it. The jet features there have been enhanced using a spatial filtering process to show you where they are. If you were to take a picture of this in time-lapse, you would actually see these jets rotate with the comet. It would look very similar to a lawn sprinkler. Now, however gases are produced, be it through jets or through diffuse emission, the neutral gases, that is just the plain compounds that come off the surface through evaporation, are the things that make up what we call the comet coma. That's that diffuse round thing that I talked about at the beginning. Now, how much gas goes into the coma? It's not a small amount at all. A typical active comet will produce something like 10 to the 29 to 10 to the 30th water atoms or water molecules per second. How much is that? Well, that's the equivalent of 5,000 gallons of water every second, enough to fill a small backyard pool. Now, every comet that gets close to the sun and is very active is going to produce that much water every second of every day for as long as it's close to the sun. That's a lot of water, but to an object 10 kilometers across, it's actually not all that much. And most comets can endure many, many passages by the sun, producing at that rate. Now, we are able to see the coma because it reflects sunlight. Now, the coma has elements of many, many different species of gas. Water makes up 90% of the mass of a comet, but it is only the most abundant of many, many compounds we can see. Most of the rest of the things that come off of comets are fairly nasty. Things like carbon dioxide, carbon monoxide, hydrogen cyanide, alcohol, aromatic hydrocarbons, and soot. Basically, the same sort of thing that comes out of the tailpipe of a car that's burning oil. Each of these gases is going to reflect sunlight in a different way, and each of them are going to interact with sunlight in a different way. Some are destroyed by sunlight rapidly. Others are formed by the destruction of other compounds that make them in the coma. And others survive for a long time, simply drifting away from the comet at about half a mile per second. The important thing to understand is that when we are looking at the comet, what we're really looking at is either an aggregate of all of these things together, or if we isolate the way we look at it, in other words, the color of what we look at, we can look at specific elements of the comet. Now, in the overhead that I have up right now, I have 3 different pictures of Comet Hyakutake. On the left, I have a picture of Comet Hyakutake in a special filter that is designed to see only dust grains in the coma. You can see that there is a shape that has a sort of fan-like direction pointing, in this case, toward the sun. In the middle picture, we have another image that also is isolating cyanogen, which is carbon and nitrogen combined. And in the third picture, we have a picture of the cyanogen after having removed the dust. As you can see, the structure of the coma looks totally different depending on which element of it we happen to be looking at a given time. Now, in some cases, the coma appears small because the molecules are destroyed by sunlight very quickly. That's the case with cyanogen. It doesn't last very far. Field of view of the images that you were looking at in the last frame are only a few thousand kilometers across. However, other species can survive for a very long time, and when we look at them, the coma is very large. The picture in the lower right here is a picture of Comet Hale-Bopp. Now, if you look in the very, very center of that, you'll see what most people saw when they looked at the comet, which was the twin tails of it. And down at the right-hand corner, you'll see a little yellow dot. The blue is the coma of Hale-Bopp in hydrogen as it was seen by the SOHO spacecraft. The yellow dot is the angular diameter of the Sun as seen from the Earth. The coma of Hale-Bopp was actually more than 10 million kilometers across when looked at in the light of hydrogen. Moving on to the second visible element of a comet coma, we come to a specific case of what can happen to a volatile gas when it's exposed to solar ultraviolet radiation. Now, occasionally ultraviolet radiation will break apart molecules. Sometimes that breaking apart of molecules will result in them becoming different molecules or breaking down into their constituent atoms. Still other times, that radiation will kick an electron off of that molecule, forming an ion. Now, ions, when they're produced in the solar system, will begin to experience the effects of being in proximity with the solar wind. Now, the solar wind is a stream of charged particles that's produced by the sun and flung outward at more than 400 miles per second. It's a very rapid flow, and it is carrying a component of the solar magnetic field with it. When the ions in the comet experience the presence of this magnetic field, they feel compelled to be pulled along, and they are accelerated up to the speed of the solar wind and dragged away. The pictures above are 3 images of the ion tail of Comet Mircos. And the ion tail is what this truly is. It's a stream of ions being dragged away from the nucleus by the solar wind. You can see the streamy nature of what's happening there, and it represents the diffuse and compact structures in the solar wind being manifested through the ions in the tail. The 2 primary components of a comet ion tail are carbon monoxide plus and H2O plus, the 2 most abundant elements of a comet's ice complement. The final element of what we think of when we're talking about a comet is formed from the trail of larger debris that are produced in the wake of the comet. The comets produce small dust grains. Those are what are blown off when you have outgassing at the nucleus, either through jets or diffusely. But there are also other processes that produce debris. Small pieces of the comet will break away as the underlying ices are destroyed. Other pieces will crack off from the surface as day-night transitions happen as the comet rotates. And still in other cases, comets will just simply blow off large pieces under outbursts of large activity. These larger pieces will not move away with the coma, but rather they will tend to spread out along the orbit behind the comet. These pieces themselves are not very cohesive, and they begin to disintegrate on their own. The smaller grains that are produced by that are literally pushed back by sunlight or radiation pressure. When this happens, it produces a great spray of dusty material that extends back along the orbit of the comet. We call this structure the dust tail. Now, the extent of the dust tail is going to depend somewhat on the cohesiveness of the nucleus. A non-cohesive nucleus will produce lots of debris as the comet melts, whereas a tightly cohesive nucleus may not. In an extreme case, some force, be it gravity or age of the comet or proximity to the sun, may force the nucleus to disrupt altogether, and all of the nucleus will go into the dust tail, which will quickly die. 2 recent examples of something like this that's happened are the comet Shoemaker-Levy 9, which was broken apart by Jupiter on its way around before it came back and hit it in 1994, and last summer, comet Linear S4, which broke up just as it was passing by the Earth on its way toward the sun. So finally, if you look in this overhead that I have here, we are looking at all of the components of the comet, including the dust tail, the ion tail, the gas jets, the coma, and the orbital and solar directions. Now, most people don't realize that a comet has more than one tail, and the reason for that is that the orbit of comets typically direct them so that the direction along the orbit and the direction to the sun are the same. In that case, the ion and dust tails overlap. But as you can see in this picture below, which is of Hale-Bopp, when they don't overlap, the tails can be widely separated. The tail at the top, which is blue, is the ion tail. The tail at the bottom, which is white, is the dust tail. And with this picture, let's move on to our next topic, which is where do comets come from? Now, it should be pretty clear, based on my description of how much water is evaporated from the surface of a comet, that an object like that probably didn't form in the inner solar system along with the Earth, and it certainly can't stay here for any extended period of time. So, how did it get here? Well, that's an interesting question, and it tells us a lot about the way the solar system formed and the way it evolved. If we do a quick inventory of the outer solar system, it will show us that comets have the most in common with the moons of the planets at the far edge of the solar system. Planets like Jupiter, Saturn, Uranus, and Neptune all have moons that are icy, very similar to comets. And actually, we've been able to do better than that from that piece of information. As you can see in the left-hand side of this overhead, we have been able to isolate where we believe comets are coming from to two areas, one referred to as the Kuiper belt and the other referred to as the Oort cloud. Of course, knowing where comets came from and knowing how they got there are two very different things. And as it turns out, the answer to that question is fundamental to everything that we're going to be covering here about the origins of the solar system and comets' role in that. It has to do a lot with the formation of planetary systems. Here's one of my favorite pictures from the Hubble Space Telescope. It's a picture of the Eagle Nebula. Now, the Eagle Nebula is a star-forming region. The spires that you see in this frame are spires of dust and gas, deep inside which stars are beginning to form. Some external perturbation, a supernova or a passing star or some object, will trigger the collapse of a cloud inside the Eagle Nebula, or in our case, whatever nebula in which the sun formed. When that happens, the material begins to collapse. The picture at left is a picture of a forming star called Beta Pictoris. Now, we have blacked out the star itself. That's the dark spot in the center of this. But what you're seeing here are the early stages of planetary system formation. As the star collapses, most of the material is pushed into the star itself. But a swirling plate of gas forms around it, a small amount compared to the star, but very significant in terms of forming planets. We call this region a protoplanetary disk. And as we see in Beta Pictoris, we are finding more and more of these as we look at nearby stars that happen to be in the early stages of formation. Within the protoplanetary disk, material will begin to accumulate rapidly. Like a snowball rolling downhill, small grains will begin to coalesce together, rapidly accumulating ices or other dust, forming larger and larger objects as more and more material is accumulated. Eventually, you have a sea of trillions of icy or rocky objects that occupy the ranges and sizes from boulders up to miniature planets, and they extend from the innermost regions of the protoplanetary disk to the outermost regions of the planetary disk. We call these smaller bodies planetesimals. We call the larger ones protoplanets. Planetesimals took on different forms depending on where they were formed inside the protoplanetary disk. In the inner solar system, where ices and other gases were not being held and were pushed away by the heat generated by the forming sun, the planetesimals are stony and solid. They contain very little mass as well. In the colder outer regions of the solar system, ices and gases are much more abundant, and they produce positively phenomenal numbers of planetesimals, much more than in the inner solar system. As we will see, this much more than in the inner solar system is going to be reflected in the sizes of the planets that are formed by the material that you get. Eventually, the protoplanets and the planetesimals will begin to combine to make objects big enough to form their own accretion disks, or protoplanetary disks. And the major planets that we know today would have been born. The leftover planetesimals are known today by more common terms. Those that were formed in the inner solar system are referred to as asteroids, or minor planets. Those that formed in the outer solar system and were left over are the comets and the Kuiper belt objects. But how exactly did the comets and the asteroids get to the specific places that we find them today? Once again, the planets are responsible. As the planets became larger, they began to gravitationally perturb the comets and the asteroids, sending many of them out of the solar system altogether. Still others were deflected in other directions. In fact, you can break down the distribution of where the objects went based on 4 possible outcomes. Number 1, they could have been thrown directly into the sun by that interaction, either being burned up by the sun or colliding with another object. They could have been accreted onto the planets. They could also have been deflected out of the solar system altogether, as I said. And indeed, this was the fate of the largest number of the remnant planetesimals. And finally, they could have been diverted to stable but far more distant orbits. Following this dispersal phase, the small percentage of remaining planetesimals occupied only 3 regions of our solar system. The innermost one is the asteroid belt, which is a region of dynamically stable orbits that are not perturbed sufficiently by the planets to force them out. The second is the Kuiper belt, again a dynamically stable region occupied by comets and Kuiper belt objects that exists just beyond the orbit of Neptune. And the third region is the Oort cloud. The Oort cloud represents the 4th class of comet, or 4th class of outcome. It is consisted entirely of objects that were thrown out of the solar system by their interaction with the planets. This new information allows us to look back at that earlier picture that I had in a new light. The Kuiper belt now appears to really just be a collection of material that never was able to form into planets. This region includes some very large members, the largest of which is Pluto. The Oort cloud, however, consists of objects from the planet-forming regions that were thrown into orbits so distant that they are up to 20% of the way to the nearest star. That's a considerable distance. However, there's a sort of ironic nature to the Oort cloud as well. Because the Oort cloud is made up of comets that were formed in the inner solar system around the orbit of Jupiter or Saturn or Uranus, and then deflected out, even though they are many, many orders of magnitude farther away from the Sun today than the Kuiper belt, they actually were formed closer to the Sun than those objects. So a question you might want to consider at this point. If all of the remaining planetesimals are in stable orbits, why do we see comets in the inner solar system today? After all, aren't they safe and steady where they are? Well, in a relative sense, they still are very safe and steady. We don't see them anymore, at least not in the numbers that we once did. In the early solar system's history, there were far more comets in the inner solar system than there are today. Perhaps there were 1,000 Hale-Bops present at any given time. That would have made a very spectacular night sky, but a very harrowing time to be alive. During that era, the Earth was being struck by objects like Hale-Bop at a rate of about once every century. That's about 100,000 times more frequently than they hit the Earth today. Now, while comets used to be deflected into the solar system by the motion of the planets, we still have to have a mechanism for getting what few we have here today. And the answer to that seems to be some sort of a cosmic lottery. The Oort cloud and the Kuiper belt contain literally hundreds of billions of members. While these objects are widely spaced and almost never come into contact with one another, when you have that many objects, occasionally 2 of them will find their way together. And when they do, they will gravitationally interact. The result of this is always the same. One object ends up getting thrown out of the solar system altogether. Are you noticing now? This is happening quite a bit more than it seems. The other one is getting deflected in toward the Sun. This is the one we're going to see. So for every comet we see, one comet has been lost to the solar system forever. Now here's a question to consider again. If so many of the comets have been thrown out of forming star systems, how will we know if a new comet is an Oort cloud object or just a passing friend from another star system that was thrown out billions and billions of years before? The truth of the matter is, we don't actually know at this point how to tell the difference between comets formed in our planetary system and those formed elsewhere. Makes for an interesting study. Now, once a comet enters the solar system, it's obviously not going to be flying in the same way the planets do. They orbit the sun in more or less circular manner at the same distance from the sun all the time. But an object from the Kuiper belt or from the Oort cloud has to come from a great distance in close to the sun. That type of orbit is very distinctive. It's an elliptical shape, much more so than any of the other planets, that carries it very close to the sun where it melts for a while, and then carries it back out where it came from. Now, the nature of orbits is such that if you are in an elliptical orbit, you spend the least amount of time when you're closest to the object that you're orbiting, so that most comets spend most of their time in the cold outer reaches of the solar system where they don't melt. That's their saving grace. This allows them to return many, many times and not evaporate away completely. The other thing that you might want to notice when you look at the picture of comet Hyakutaki's orbit, which is what's to the left in this frame, you will notice that the orbit is not inclined to the same plane as the orbits of the other planets. Indeed, Hyakutaki was a polar comet. It went over the north pole of the sun, whereas most of the planets orbit around the sun's equator. This is a nature of Oort cloud comets, which are more or less randomly distributed around the sun. Now, if the orbit of a comet never did anything except return over and over again, they would take an enormously long period of time to return after every apparition. They would also evolve very, very slowly. We would never see comets more than once, because most of their periods would be many tens of thousands of years long. Yet we see many comets return over and over again. The reason why this is that the comets, when they come into the inner solar system, expose themselves once again to the gravitational perturbations of the other planets. Comets, as you can see in the picture below, that encounter another planet will have their orbit modified. In this case, we are looking at a comet that is coming from the Oort cloud, encountering a planet, and having its orbit redistributed so that it no longer moves any farther away than the planet's orbit around the sun. If that planet is the Earth, that comet is in trouble. It's going to be sitting in that place and melting very quickly and will not last very long. We call objects that get into orbits like this short period comets, and they include the most famous comet of all, 1P Halley, the comet that was first used to identify that these objects were orbiting the sun and returned periodically. There are more than 150 short period comets that we routinely track. These objects have periods anywhere from a few hundred years to as short as 3.3 years, which is a relatively famous comet called Encke. They are very important, the short period comets, because they are the only ones that we can predict when they're going to appear. And by predicting them, we can plan our studies. This makes them more effective in terms of visiting with spacecraft as well. Now, short period comets will leave a well-worn trail of dust in their wake. Occasionally, the Earth will pass through this trail of dust. And when it does, we will be treated to a meteor shower of tiny dust grains. Two very famous meteor showers that happen every year are the Leonids and the Perseids. And when someone tells you to go look at that, what you are looking at are tiny grains of dust liberated by those comets anywhere from the last few years to the last few thousand years. So, by now we know a few things. We know what the different parts of a comet are. We know where they came from. We know how they formed. And we know what their orbits and life cycles are like. So you might ask now, why do we need to continue to study them? In fact, the reason is that they are among the most scientifically important objects. There are many avenues of research to pursue with comets. And just knowing where they came from, or what the different aspects of them are, is only setting the table for the study. Now we go in and try to understand why they are what they are. The most important element of comets from our perspective, as an origins lecture today, is that comets, quite literally, are time machines. Unlike every other object in the solar system, comets are more or less exactly the way they were at the time the sun turned on 4.5 billion years ago. All of the planets, even the asteroids, have really been modified since that time. Their surfaces have been changed. their internal workings have been processed. None of them are what they were when the solar system formed. And indeed, the original nature of comets extends even further back than that. It carries with them information about the temperature, the density, and the composition of the cloud that collapsed to form the solar system that we see today. The second way in which comets are interesting to us is as astrophysical probes. Because they retain that information about the cloud out of which the solar system formed, that means that they contain at least some template of information about the clouds that we see in a galaxy today, and if not in our galaxy, in other galaxies as well. Look at the picture to the left in this frame. It's a picture of a galaxy that has been observed by the Hubble telescope edge on. The brown strip that you see through the middle of it is not a gap in the stars. It's dust and gas between those stars, and it is out of that dust and gas that new star systems will be formed. This material is referred to as the interstellar medium, and it is remote and it is unchanging on timescales that matter to us. This makes studying it very difficult because we can only look at each interstellar cloud from one perspective in one instant of its history. But comets present us with an opportunity. They are primordial objects that contain information about the interstellar medium at a frozen point in time 4.5 billion years ago in the region of our galaxy where our sun formed. When they approach the sun, they melt, and they reliberate the material that once made up the interstellar medium. We get to see that material under a range of conditions, different temperatures, different outgassing rates, different compositions, different dust compositions. All of these things are available to us if we observe comets. Now, this is the reason behind several of the missions that people have been proposing and enacting at NASA over the last several years. Two that you may have heard about are the currently operating Stardust mission, whose purpose is to go and retrieve dust from a comet, and the soon-to-be-flown Contour mission, which will fly past the nuclei of 3 comets in the first decade of this century. A third area in which comets are interesting to us is in the study of the solar wind and the solar radiation field. Observations of the neutral coma and the ion tail provide us with an opportunity to study the production of charged particles from the sun and energetic solar radiation as it interacts with that material. Now, we can't see the radiation from the sun that's emitted in the extreme and the far ultraviolet because our atmosphere, for the most part, absorbs it, and we don't get to see it. Nevertheless, those emissions are there, and they drive chemistry in our upper atmosphere. And they also play an important role in those parts of our world where the ozone layer has become depleted. We need to understand the solar radiation field at these wavelengths. To the left, you can see a picture that is taken in the X-ray by the SOHO spacecraft. It's taking pictures of the sun at this wavelength and at other wavelengths. But without the SOHO there, comets provide us with an opportunity to study this sort of radiation. From our basic knowledge of chemical processes, we are able to study the photochemical evolution of the materials in the coma to back out the characteristics of the solar radiation field. In the picture at the left here, it's another SOHO image of streaming charged particles moving away from the sun. These charged particles are what we call the solar wind. The solar wind is an enormously important thing in our technological age. Until perhaps 100 years ago, they provided us with one thing and one thing only, and that was an impressive display called the aurora borealis. These charged particles interact with the terrestrial magnetic field and produce most of what we experience as space weather in the area immediately above the Earth. The solar wind has 4 very important consequences for the modern technological world that we need to take into account. First, solar wind activity interacting with the Earth's atmosphere will tend to heat it. When the Earth's atmosphere is heated, it expands, and satellites that are in low Earth orbit will experience greater drag than they would at other times. Secondly, these charged particles when they penetrate to the inner Earth's magnetosphere, begin to interfere with microprocessors and other sensitive equipment on existing communications, weather, and other satellites. This can have broad consequences for our life here on Earth. A third area in which they can have a significant effect is in generating activity in the Earth's upper atmosphere, what we call the ionosphere. When the solar wind interacts with the Earth's atmosphere through the auroras, it can create electromagnetic disturbances which produce problems with communications and other electronic equipment. So if we need to understand the solar wind, one good way to do it is to study comets. Because by studying the interaction of a comet ion tail with the solar wind, we are actually getting information about the density and velocity of the solar wind that's interacting with it. This is hard to do with existing spacecraft. We have only a few instruments that are able to measure the solar wind at any given location, and comets represent a windsock in that flow. Now, the other advantage of comets is that they move very quickly through the solar system. And as they move through the solar system, they sample the solar wind at different locations, and often out of the inclination of the planet orbits. All of this is important to our understanding of the solar wind and how the sun generates this flow. Finally, an important area of scientific understanding that comets contribute to is helping us to understand about ourselves. While they didn't form near the Earth, and they would certainly have been destroyed after a short visit to our location, comets have played an important part in why we are here today. Keep in mind, when I describe the formation of planetesimals in the inner solar system, I didn't talk about ices or water or gases. I talked about stones and rocks. And indeed, the terrestrial planets are almost entirely composed of stones and rocks. If that's the case, then where did the oceans and the atmosphere that we need to survive come from? Could they have come from comets? It's possible. We are not sure. The way in which this would have happened is during the dispersal phase, when I told you earlier that the Earth was being pelted by objects of the size of Comet Hale-Bopp once every century. Well, the dispersal phase was quite long, and if you add up all the time during which comets were flying through the inner solar system as they were being flung away by the planets, and you added them up at one per century, more than 1 million objects the size of Hale-Bopp would have hit the Earth. That's an awful lot of water, that's an awful lot of gas, enough to form oceans and an atmosphere. Now, scientists are divided about whether or not this scenario actually describes the manner in which we got oceans on the surface of the Earth. Other mechanisms have been described, and it is thought possibly that comets simply boiled off as soon as they hit. We don't know the answers yet, and hopefully we will soon. But there are some researchers that attribute an even more expansive role to comets in the life cycle of the solar system. Adherents of a concept called panspermia believe that life itself evolved first in comets and is carried by them throughout the universe. In this scenario, the Earth itself was a sterile environment until comets hit it, and when they hit the Earth, they imparted the living things that were embedded within it, and it is from those that all living things on the Earth have evolved. One consequence of panspermia would be that if we explored the rest of the solar system and were to discover life, in a panspermic universe, all that life would be virtually identical to us, at least at a cellular level. And finally, one area that all people seem to be paying attention to as an area of scientific interest for comets is that they themselves pose a threat to us. The history of our world is very clear. Over geologic time, there have been periodic impacts of large bodies that have altered the environment in such a way that it has pushed evolution in different directions. The most famous of these events is the KT impactor that occurred about 65 million years ago and wiped out the dinosaurs. That single event destroyed 70% of every species that lived on the Earth at that time. Now, impacts like that do sound terrifying, but they have played an important role in us being here today. Indeed, we probably owe our existence to the KT impactor. Without that, dinosaurs would probably still rule the Earth today. But the destruction of them by that impactor opened the way for mammals to become the dominant land animals that they are. Now, we are right to fear them now, because an impact of that nature would probably clear the way for something else to come by. But it's probably likely that even though we didn't know we were in danger of this as little as 50 years ago, within 100 years or so, we're likely to know how to deflect a comet if it comes by. Now that's wonderful news for us, and it means that we will make the Earth safe for mankind. But it doesn't mean that we are going to spare the Earth from a catastrophe similar to the KT impactor. We are currently at a pace, through simple human activity, of destroying as much as 70% of all the species that live on the Earth right now within the next century. That means that through our own paving of the streets, building of factories, simple human activities, we will achieve by ourselves within a century the same level of destruction that a comet 10 miles across hitting the Earth at 20 kilometers a second could achieve in a day. It's a sobering thought and a rather chilling reminder of the price of progress. Okay, getting away from the downer of that, I want to close with a brief discussion of the role of comets in historical and modern psyche. As I said at the beginning, imagine yourself standing on a field 2,000 years ago, seeing a comet stretching from end of the sky to the end of the sky. This is a significant event in your life. And as a result, people have always had a very, very, very profound place for comets in their lives. Perhaps only solar eclipses come across as more significant than comet events in terms of astronomical occurrences. Now, comets are kind of funny. As they come by, something always seems to be happening. Now, this is a natural event in terms of human experience. Civilization is a busy place. There's always something happening, or has just happened, or is about to happen somewhere in the world. If a comet happens to fly by at the same time, often people will attribute the comet to the cause of whatever they wish. This sort of self-fulfilling prophecy has made comets very, very dire throughout our history. A comet was in the skies over London as the Black Plague was wiping out large tracts of the city. Therefore, it was blamed for it. A comet appeared in the sky just as Napoleon was about to attack Russia. It was that driving factor, not strategic decisions, that forced him to go forward. Now you might laugh and say to yourself, yes, but we're so much more enlightened than Napoleon was. We know so much more than the British did when they were blaming comets for the Black Plague. But the truth is, technology marches on, but our ability to make fools of ourselves seems to stay a constant. Within the last 100 years, we've encountered comets multiple times. We now know where they are, we know where they come from, we know what they're made of. That hasn't stopped us from behaving stupidly about them. In 1910, Comet Halley passed very close to the Earth, and a reporter noted that we were going to pass through the tail of that comet. Now, just prior to that announcement, a scientist had pointed out that we had just discovered hydrogen cyanide in the tail of that comet. This provoked hysteria across the Earth, and snake oil salesmen were making a lot of money selling comet pills and gas masks to protect people when they passed through the poisonous comet that never killed anyone. Okay, 1910, that was a long time ago. Perhaps we're smarter today. But it doesn't seem so. Even as recently as Comet Hale-Bopp, there is the unfortunate story of the Heaven's Gate cult that committed mass suicide as the comet came by in the belief that they were going to be taken to a better place by its passage. Another comet is bound to happen at some point in the future, and we will come up with some different reason why it's an important event in our lives. The most popular today, of course, is the likelihood of collisions, which, as I pointed out, is not all that likely at all. In fact, during the next 100 years, our chances of being hit by a comet and killed are somewhere in the neighborhood of 1 in 100,000. There are definitely more pressing concerns than this, and I don't think we need to worry about it. Well, that concludes my discussion of comets today. I want to thank you for listening in. I hope you learned something, and I hope you enjoyed the talk. Bye.
Thank you very much, Dr. Harris, for that wonderful talk. I'm particularly intrigued by the theory that the oceans and atmosphere of the Earth might have been formed with incoming comets. I'm wondering if you could enlighten the audience as far as the more well-accepted theories that are out there.
Well, there are multiple theories as to what formed the comet, or what formed the oceans and the atmosphere. And that comets may have played a role in that is certainly undeniable. What we don't know is how much different elements played. Oceans and the atmosphere on the Earth make only a very, very, very small percentage of the total amount of mass of the planet. And so it's possible that a small amount of volatile material, like water or gases, may have been trapped in the planetesimals that formed the Earth in the first place, and then were subsequently outgassed by volcanic activity early in our history. That was the accepted idea before it became clear how often comets were hitting the Earth early in our history. Once it became clear that as many as 1 million comets might have hit the Earth, it suddenly became more possible that comets are playing a role. Now, the chief way in which we have been attempting to answer this question is by looking at the deuterium to hydrogen ratio in these comets. That's a characteristic of the comets themselves. And if we compare the comets to the oceans that we have today, it should give us a clue as to whether or not the water in those oceans is the same as the water in comets. The problem is we only have 3 comets that we've done this measurement on. So I would say that the answer is very incomplete.
Good. Thank you.
I'd like to also say thank you for such a fascinating talk. I learned a lot. But I do have a question. Since comets melt when their orbit brings them close to the sun, we know that. Do some or all of the short period comets have known or expected expiration dates?
Well, that is a good question. I don't think we know the answer. I would say no. The short period comets are by definition less active because they have been around for a long time, and they have lost a lot of the volatiles that are easily accessible at their surface. What will happen to a comet over time is, well, something rather similar to what's happening right now in early spring, when you go to a shopping mall and you see a big pile of snow. Now, a week and a half ago, when it was fairly cold out, that big pile of snow was white with some dirt on top of it. Well, it's now considerably smaller, and it's considerably dirtier. Well, the same thing's happening on a comet. It's melting away the ices, but the rocks and the pebbles that are on top are still there. And so they tend to fall down and get more and more clumped over the surface of that nucleus. Eventually, a comet can actually be covered by an insulating blanket of stones and dirt that prevent any further outgassing. And a characteristic of short period comets is that occasionally they'll melt through that and outburst in some spectacular way. And we have seen that on several occasions.
Thank you.
I guess I have a question.
Okay.
Well, I guess I have 2 questions. The only difference between an asteroid and a comet then is that they're formed in different parts of the solar system?
Well, that's a primary difference. It's not the only difference. And I would say going into the specifics of what make different kinds of asteroids and different kinds of comets is probably beyond the scope of what we're really talking about here today. My point is that asteroids represented the planet building process, the basic elements of the planet building process in the inner solar system, while comets represent the basic elements of the planet building process in the outer solar system.
So Pluto, I guess, brings up the case in point right now. If Pluto is a member of the Kuiper belt, that actually be called a comet or an asteroid? Or how did it form?
Well, that comes back into something other than the definition of what a comet is. That's a question of what is the definition of a planet. There's no doubt that Pluto bears a common heritage with the remaining members of the Kuiper Belt. They all formed under more or less the same process. And if you want to be technical about it, I suppose you should group Pluto in with the rest of the Kuiper Belt objects, just as a particularly big one. In fact, I don't think we can exclude the possibility that we will find objects larger than Pluto in the Kuiper Belt. We simply haven't looked hard enough. But I think it's probably fair to continue to call Pluto a planet just because of its historical significance. It's been a planet for 60 years. We don't really have a hard and fast definition of what a planet is, and I think it would probably diminish the history of it a little bit to downgrade it in that way. And I should point out that there's an analogous object in the inner solar system that represents the extreme end of asteroid formation, and that is the asteroid Ceres, which is almost as large as Pluto and was actually discovered and tentatively identified as a planet. The difference being that they quickly realized how small it probably was and redesignated it as a minor planet shortly afterwards. So it's really a semantic argument.
Okay. Thank you for that clarification. But I mean, to a layman, Pluto could be a comet, a planet, or an asteroid.
That's right.
Okay. My second question had to do with what comets tell us about galaxy. In one of your early slides, you talked about comets tell us about the evolution of the solar system. What do they really tell us about the galaxy?
Oh, well, what they tell us about the galaxy is they tell us about the structure of that material that we saw in that brown strip of that picture earlier. It's telling us about the interstellar medium. It's the material between the stars. That makes up a substantial fraction of the total mass of our galaxy, and it is the material out of which all the stars that we see in the galaxy today and all the stars that are going to be in the galaxy in the next several billion years will form. So if we want to understand that material, and we do, then we need to understand something that's made of that material. Now, everything in our solar system is made of that material, but it's been processed. The atmospheres have changed, the planets have differentiated. Things are different after 4 billion years. But in the case of the comets, they truly carry the composition, the density, the temperature, and the dust structure of that early interstellar medium. Is it a perfect answer? It's not, because that's going to be different in different parts of the galaxy, but it's clearly the best opportunity that we get to look at this sort of thing.
I think that's the last question I had. Thank you for a wonderful lecture. It was very...
I was happy to be here. I enjoyed it.
Thanks.